Hello everyone, this is Faisal Alamri. In this presentation, I will present our paper titled as Implicit and Explicit Attention for Zero-Shot Learning. Zero-shot learning aims to recognize a set of classes known as unseen classes, which are not available in the training phase. The idea behind this is the knowledge transfer, where the transfer learning occurs with the help of the semantic of information. In our case, attributes are used as the semantic information which describe both seen and unseen classes. Therefore, zero-shot learning is employed to bridge the gap between these two sets of classes. In zero-shot learning, there are two training protocols, which are inductive and transductive. Our proposed method follows the inductive setting, meaning that the model has access only to the seen classes information. In terms of the testing phase, there are also two settings. The first one is to recognize unseen classes, which is known as zero-shot learning. The second, which our method follows, is called generalized zero-shot learning, which is to recognize both seen and unseen classes. In terms of our proposed method, as we can see in this figure, we have two sets of images. The first is denoted as S, which includes the seen classes images and semantic information. The second is denoted as A, which contains the rotated images. We examine the effectiveness of our method using two different backbones, which are Resonate 101 and the Vision Transformer. As shown in green, seen classes images and attributes are used to train the model to predict class attributes with the help of mean squared error. However, as in blue, rotated images are used for rotation angle classification, which helps the model to learn visual representations with the help of implicit attention mechanism. In explicit attention, the model attends to image regions and learns the visual features that can be relevant to predict attributes with the help of multi-head self-attention that is employed in the Vision Transformer. On the other hand, in the implicit attention, the model predicts the rotation angle and captures the visual features implicitly in a self-supervised approach. In the testing phase, the model predicts attributes where cosine similarity between the predicted attributes and every class embedding is computed, which is then used to predict the class label. In our experiments, we have used three datasets, which are AWA2, CUP, and SUN. Please refer to our paper for more information about these datasets. In terms of the evaluation matrix, harmonic mean is used to evaluate and compare our model with the state of the art, as presented next. We compared our method employed on both Resonate and the Vision Transformer with 18 different models, 4 of which are generative and the rest are discriminative as the proposed method. Clearly, we can see that our method achieves the best scores in terms of seen and unseen classes for the majority of the datasets, leading to achieve the best harmonic mean among all the datasets. we tested our method on both ResNet and Vision Transformer without the use of rotated images, and found that models are biased towards scene classes. However, when the models are trained in a self-supervised approach, including the rotated images, the performance increased and the bias issue was reduced. We have some more results where we have included different images as the rotated images to examine the effectiveness of our method on different sets of images. We observe that the inclusion of unlabeled images from unseen classes significantly improves the performance on all the data sets. We also observe that including images from data sets such as Pascal improves the performance and increase generalization. Clearly, we can see that our model attends to object attributes. The model has learned to map the relevant local regions to the attributes. Our model improves the performance as we can notice more relevant local attributes are highlighted. In the conclusion, as presented, our method achieves the best performance among the state-of-the-art models on 3 datasets. It combines the implicit and explicit attention mechanism to learn and attend to the relevant object parts in a decorrelated and independent way. We believe including the rotation angle recognition in a self-supervised approach with the use of the Vision Transformer does not only improve the performance, but also, and more importantly, contributes to reduce the bias issue towards scene classes. We expect the bias issue to be reduced even further if our model is trained in a generative approach, which we left as our future work. Thank you for listening. For more information about our method and implementation, please visit our paper.